All right, we're back with another lesson, 16.8. This one's going to be about protein hydrolysis and protein denaturation. So basically, how do proteins get broken down? And they can be broken down or altered in two different ways. The first way is by protein hydrolysis. That word hydrolysis means to split something using water. And if you remember the carbohydrates, we talked about that there, so it's going to be very similar. The other way to change a protein or break it down, if you will, is by denaturing it. So it wants to be in this natural state. Well, you denature it. It's a very common term for proteins. Then you've broken down the protein. This is actually really common. Protein denaturation is a very common term. We talk about proteins being denatured. That's usually referring to the breaking down of proteins, and that's the term that's often used. All right, but you'll see that is actually not actually tearing apart the protein necessarily, whereas protein hydrolysis is kind of more impactful. You're actually breaking it apart and opening it up. And so, in fact, let's go ahead and just talk about that now real quick while we have it here. So for the first one, with protein hydrolysis, you're actually affecting the primary structure of a protein. You are literally breaking the peptide bonds or the amide bonds, whatever you want to call them. You're breaking those bonds and separating the amino acids so that they're back in their individual amino acid form again. And that I mean, you can't get any further than that. Well, you can actually break down the amino acids for other chemical reactions and break those down even further. But as far as proteins go, that's pretty big. You're affecting the primary structure. It's done. We don't even call it a peptide anymore. The other type of breaking down of proteins, which is more common, is the changing of the shape of proteins. And so, if you remember, a lot goes into twisting and folding and changing the shape of a protein by all the interactions between the side chains of the amino acids. And so because of that, if you alter that, if you mess any of that up, then you are going to denature the protein and affect the secondary, tertiary, and quaternary structures. Okay, anything that you're doing at this level is secondary, tertiary, and quaternary. You're messing up the shape. But actually, the polypeptide is still intact. All the amino acids are still connected to each other via peptide bonds. And so it begs the question, if you bring things back to their natural state, can the protein go back to its original form? Probably. That question just came to my mind, so I'd have to do further research. But I know with certain proteins, like eggs, once you cook an egg, you're not going to get the proteins back to the way they were. Actually, you could. Could you? Maybe, with enough heat in the right circumstances. But generally, no. So, okay, so let's get into it now. I'm going to go ahead and just switch to my computer here. So you can see we have 16.A is about the protein hydrolysis. And basically, it's going to be the treatment with water, but now that's also going to happen usually with an acid, base, or certain enzyme as well. But the key ingredient that's going to do this is H2O. You can see that here, and here. Okay, water. Water is going to come in here and break the peptide bonds. And how does it do it? Well, if you remember, it's going to donate an O to one and an OH to another. I'm sorry, an OH to one and an H to another. So if we look here carefully, we can actually see what's going on. The amide bond or the peptide bond is this carbon-nitrogen bond, do you remember? And this would be the C-terminal end of this just amino acid here. This would be the inside, the N-terminal side. And now what's going to happen is once we break this bond, remember what used to be there? An OH, right? And so you've got to put an OH there. And we do, but actually since the H that was there with the OH has gone over here to make the NH2, NH3, you remember that happens, right? Hopefully you remember that. The acid-base behavior of amino acids. Naturally, they don't exist with a carboxylic acid here and an NH2. What happens is that H on the OH, let's just scroll up and look at that real quick because it's very relevant here. So what actually happens here is the H here that's on the carboxylic acid gets transferred over to here, leaving you with a Zwitter ion. A Zwitter ion. Remember that funny word? And that ends up leaving a negative charge on this side of the Zwitter ion and a positive charge on this side of the Zwitter ion. But it's still all one molecule, so it's not technically like an ionic compound. It's still, these are all covalent bonds, but it almost is very polar and having a positive side and a negative side. That's actually the way amino acids really exist in nature. Okay. And so we're going to reestablish this side, and we're going to reestablish this side for those amino acids after we're done with hydrolysis. So we scroll down and look again, and we see that all we need to put there is an oxygen. And so there you go. And all we need to put here with this NH is 2 hydrogens to leave you with that NH3. And then same thing for this carbon and nitrogen bond. This peptide bond will do the same thing. We'll attach an oxygen to this carbon here, so that there's an oxygen hanging off. There it is, you can see it. And then on the NH2 of this amino acid, we'll add 2 more hydrogens. So we'll have NH3. And then again, this O is already there. Okay, that O is already there. So all these amino acids, which would be isoleucine, glycine, and phenylalanine, all of them are back in their Zwitter ion, just independent forms floating around. And these amino acids are like Legos for the body, and the body will reassemble them into other proteins, or it could even break them down for energy, but usually it'll just collect them and have them ready to assemble new proteins when needed. And so let's talk about how does that happen again. The first step in digestion of a dietary protein is literally the hydrolysis of those amino acids. So if you're going to break down a protein for digestion, for energy, you're going to use hydrolysis to break those amide bonds or peptide bonds. All right, and then the enzyme pepsin in the acidic gastric juices of the stomach is what cleaves some of those amide bonds to form smaller peptides. So this already happens right away in your stomach. So as soon as food gets into your stomach, you have an enzyme called pepsin, which is going to be the key player there that allows that to happen. The enzyme pepsin in your gastric juices are going to break those bonds. And then once your food gets passed from your stomach into your small intestines, which you remember from biology is where all your absorption happens. The stomach is just churns and turns. It just breaks your food down into smaller pieces. But you don't actually really, there's no blood vessels that are surrounding your stomach that do a lot of absorption. There's blood, vessels supplying oxygen to your stomach, the cells in your stomach. Every cell needs, circulatory system to it. It needs to be connected, even neurons. Every cell needs a connection there, but that's not really where absorption happens. All that takes place in the small intestines, which is a long passageway, and it takes a long time, so that's why it's long. So you have plenty of time to absorb all your nutrients. And in the small intestines, that's where you're further going to break down the amino acids using trypsin and chymotrypsin. Those are 2 enzymes that you'll use to break down amino acids in your intestines. Okay, and proteins, again, can also be used for nutritional needs. When we say nutritional, what we mean is like for energy, just like carbohydrates and lipids. Proteins can also be metabolized for energy. They're not just for, I know we've kind of done a lot of talk, especially in the last lecture, how proteins are so good for structure and for doing things like functions, like being an enzyme or something like that. But they can actually be broken down for energy too. You get about as much energy out of a protein as you do carbohydrates, believe it or not. It's like 4 grams or 4 calories per gram for both. Fats, you get 9 calories per gram, so way more energy storage there. But okay, so moreover, the individual amino acids that are that are formed at least after hydrolysis, again, they're going to be used as like building blocks for the next proteins. But another thing that could happen is even the nitrogen atoms could be taken out and put onto other biological molecules, because amino acids are not the only molecules in your body that contain nitrogen. Nitrogen's a common biological element. Okay, draw the structures. Here's a sample problem, and then there's two of yours to do. Draw structures of amino acids formed by the hydrolysis of the neuropeptide leuenkephalin. You remember enkephalins? Those are the painkillers. Back when we were looking at peptides, you remember with peptides, not quite a protein yet. You're not quite a protein yet, but peptides, you can have dipeptides or tripeptides, and here's a this is a peptide, I'm sorry, that goes beyond di or tri. There's actually 5 amino acids in these peptides, but they're still considered peptides. They're not considered full-on proteins yet. You got to do all the other levels of structure to be a protein. So, excuse me, I was wrong. There's not just dipeptides and tripeptides. But these peptides are neuropeptides. If you remember, they're kind of like painkillers. And they had 2 different types of enkephalins. We had methionine, or that's abbreviation for methionine. So we have metenkephalin and leuenkephalin. So in other words, it's either methionine enkephalin or leucine enkephalin. And basically the difference is this methionine here or this leucine here. The rest of these amino acids are the same. You see it starts out tyrosine, glycine, glycine, phenylalanine, tyrosine, glycine, glycine, phenylalanine. But if the C-terminal end over here, if the C-terminal end of the polypeptide is methionine, then it's metenkephalin. If the C-terminal end is leucine, then it's leuenkephalin. Well, if we take leuenkephalin, that's the problem we're working on right now. If we take leuenkephalin and we hydrolyze all of these peptide bonds here, all the carbon-nitrogen bonds that are bonding these peptides together, what will we end up with? Well, you'll end up with these amino acids. So you could cheat and just go back to this table here, and there they all are, or there they are there, or there they are there. Or it's pretty simple. Hydrolysis is so easy. You're literally putting an oxygen there and the other 2 H's there. An oxygen there and the other 2 H's there. And so in this problem, again, we're going to be putting an oxygen with that carbon, so there it is. And then we're going to be putting 2 hydrogens with that NH, so it's now NH3. And now don't forget the little formal charges. Those are important. If you don't put a formal charge, people are going to make fun of you. So make sure you put those formal charges so people will take you seriously, especially me when I'm grading your stuff. All right, now, so basically we just have these tyrosine, glycine, glycine, phenylalanine, and leucine drawn out how you would see them normally in nature. That's it. Pretty simple, right? Again, the key takeaway is that with protein hydrolysis, you're messing up the individual amino acid sequences. That's the primary structure. That's the first level of organization of a protein. Once you've done that, you're back at literally square zero, if you ask me. Now, protein denaturation, though, you're only changing the shape. So consider a globular protein like this. If you heat it up, well, all those interactions between the side chains that made all of these helixes or sheets, or there's a whole list of them, right? If you remember this picture here, awesome picture, I love this. You should have something like this in your notes when you go to biochemistry in college. Just a nice little cheat sheet here. It kind of has all the different interactions. Whatever it is, whether it's an electrostatic attraction like this, an ionic attraction, whether it's a hydrogen bond here, or whether it's a London dispersion force, which is just a weak force between nonpolar substances, very weak. Now, I didn't say disulfide bond because that's actually going beyond the term attraction. It's an interaction, but it's actually a covalent bond right there. So disulfur bonds, disulfide bridges, you won't necessarily break those. unless you had considerable amount of heat. I mean, any bond can be broken, but typically when you when you unfold a protein like this so that it's all loose, you're basically just breaking up those attractions. And so here you go. Let's start at the lowest level. Heat is going to be able to be enough to break up the weak London dispersion forces, which you remember is just an attraction between nonpolar and nonpolar. Okay, so you have very weak attraction there. So, but heat can do that. Heat, acid, and base, they can disrupt hydrogen bonding, which is those are pretty strong, right? You have two polar substances attracted to each other. That's pretty strong. And so those will be disrupted by acids and bases or heat. And so that's going to account for much of the secondary and tertiary structure. Let's see. I wanted to see, did the book say anything about the ionic attractions? Interesting. I don't see that there. But even the ionic attractions are going to be disrupted as well. When it comes down to having acids and bases, you're going to mess up even the ionic bonding. All right. Okay. As a result, denaturation causes a globular protein like this to uncoil. Or it depends on what protein you're looking at. If it's a globular, then instead of being round and all balled up with all the hydrophobic stuff in the middle and the hydrophilic stuff on the outside, which is usually the case, instead of breaking all that up into a loose coil like this, you could essentially break up a fibrous protein, if you remember from the last lecture, is the other type of protein. In fact, that's what problem 16.20 asks you to do. So consider the other type of protein, the fibrous ones, and give me a good detailed sentence to answer that. You know, like what would actually happen if you heated up collagen, and like what kind of denaturation would occur, and use good vocabulary. Don't just say it changes shape. Denaturation often makes globular proteins less water soluble, because if you remember, again, for globular proteins, they should have put this here. It'd be an awesome thing to put. On the outside of globular proteins is where you're going to find most of the polar side chains, so that the globular proteins can dissolve in water. And the hydrophobic stuff likes to hang out kind of tucked deep inside the globular protein. Remember, this is very three-dimensional. We're looking at this two-dimensionally here. But and so what happens is whenever denaturation occurs, they're not as water soluble. And so what happens is, like, for example, an egg, when you break it open, a lot of it's clear, but once you denature the protein, it becomes white. You can see that before the egg even really gets that hot. Globular proteins are typically folded. Well, I already said all that. So there you go. I think that's it. Here's just another couple examples just for fun. When milk ages, it becomes sour from there's enzymes in there that will produce lactic acid. So they break up the lactose and or any of the sugars, and they produce lactic acid through you remember lactic acid is a fermentation process when you don't have oxygen present. Instead of doing glycolysis, instead of doing if you don't want to do Krebs cycle and the electron transport chain, if there's no oxygen present, then you can do either alcoholic fermentation or lactic acid fermentation. And there's bacteria that do lactic acid fermentation. And what that's going to do is denature the proteins. The lactic acid is going to denature the milk proteins. And that's why they're going to precipitate out as an insoluble curd. They won't be dissolved anymore because the hydrophobic side chains are now exposed instead of being all tucked away nice and neat inside the globular protein. Ovalbumin, which is a major protein in egg white, is denatured when you heat it up as well. Even if you whip it, which is kind of interesting. I found that neat when I started cooking at some point, or well, at least cooking with this certain type of recipes. Where, have you ever read a recipe that says to whip the eggs to a point where there's stiff peaks? I was like, what is a stiff peak? What are they talking about? Well, sure enough, and you got to have a machine to do it. If you try it with your hand, it takes forever. But if you whip it hard enough, like with a machine, the egg whites won't be liquid anymore. You don't want to do this with the yolk, by the way. Take the yolk out. But if you do just the egg whites like this, it'll turn into like literally almost, it looks like a solid. Like you could literally pick it up with your hand and throw it. But it's very airy too. There's a lot of air inside of it. And so that's a great thing to do. And then you can fold it into your pancake. I usually fold it into my waffle recipe so that my waffles are nice and fluffy. But you can also fold that into a lot of cakes or things like that. So you have a nice, good, like airy texture. Cool. Or meringue pie. That's going to be it, guys. Thanks for watching. Stay tuned for the next. We got 2 more lectures. I'm going to try to give those to you tonight.